So we're going to pick up just one piece from the last lecture when we were discussing diffusion and random walks, and I put a spreadsheet for you on Canvas to enable you to calculate random walks to get a feel for the way random behavior in diffusion can lead to systematic correlations like the Einstein relation. And so to run the simulation, the random walk, you need to enable the macros. And this is the random walk simulation, the Monte Carlo simulation that we discussed in the most recent class lecture. And so what is being shown here on the graph is the mean square displacement of a particle as a function of the number of diffusion steps, which would be equal to time, for a given number of steps, and then also for a given number of simulations. And so if we set the number of random walk steps to 25, for example, and press calculate, then we get a trajectory for a single particle over 25 diffusion steps. And this is basically picking a random number in the computer and then deciding based on that what the displacement of the particle is going to be in the plus and minus x, y, and z directions, and then calculating the mean square displacement after each of those steps. And the Einstein relation would predict that averaged over enough particles, that is enough number of simulations, that this relationship would be perfectly linear. That is, the mean square displacement would go linear with time, or equivalently, the distance away from the origin that the particle gets goes with the square root of time. And we've normalized the mean square displacement and the time or diffusion step number by the parameters that are shown in the last slides. And so with that normalization, when the Einstein equation is obeyed, this random walk should give a mean square displacement that is just exactly equal to the time or diffusion step number. And so if we calculate a second trajectory, we can see the mean square displacement has gone all the way out to not quite 20. Calculate a third one, it's a little more than 20, and you can calculate these on and on. Here's an energetic one, it's gone all the way out to 70. To keep in mind, the mean square displacement could go as high as the square of the number of random walk steps. So it could go as high as 525. And what you're seeing here is that due to the random number, the random nature of the displacements, that the particle is never getting anywhere near as far away from the origin as it would if it were traveling in a straight line linearly. And you can see in some cases like this one, it really never gets very far at all. After 25 diffusion steps, it's only has a mean square displacement of 3 units away from the start. And you can see that the number of steps in the plus and minus y direction and so forth, if this were a truly random process with large numbers, these values of steps in different directions would be almost equal to one another. And you can see that the percent deviation in the number of these steps away from the average is quite significant when the number of simulations is small. And so if we increase the number of simulations to 10, that is, we run 10 of these trajectories at once and then average them, now you see the mean square displacement still not completely linear with time or diffusion step number, but it's getting much closer, and you see these deviations in the number of steps away from the average, the percent deviation getting smaller. And so we have now 10 random walks of 25 steps per random walk, so that's a total of 250 steps. If we go ahead and raise that to 50 and run the simulation again, now you can start to see the mean square displacement really flattening out when we average over 50 of these random walks, each of which will not look anything like this, but on average they start to look more and more like the Einstein relationship. That is a straight line where the mean square displacement in these scaled coordinates is simply equal to the diffusion step number. And if we go on up to 100 of these simulations and run those, now you see the line getting straighter and straighter, and the endpoint closer and closer to 25, which would be the prediction of the Einstein equation. If we go to 200, it's a little bit under, but still quite linear. 500, and you really start to see this get closer and closer to 25, and the deviations in the number of steps in any direction, the percent deviation now is getting quite small. So we go to 1,000, and again we're getting very close to the Einstein limit. If I lengthen the number of steps per simulation, now the calculations take a while, and since I have 50 random walk steps, then my mean square displacement in the Einstein limit is going to be equal to 50 after 50 diffusion steps. And you can see that as you increase the number of steps and the number of simulations, you gradually exactly approach the Einstein relationship. That is, out of random molecular motion comes this very deterministic prediction that the mean square displacement rises linearly with time. And this is completely coherent with Fick's law, which says that out of random molecular motion, the net flux of molecules is on average from the position of high concentration, or region of high concentration, region of low concentration, and it is so regular that one can apply very rigorous differential equations to model the time and position variation of concentration in systems undergoing diffusion, even though the underlying phenomena is inherently random. And the way this works out is that when the number of particles or molecules undergoing diffusion gets large, and when they take a large number of steps, that random behavior gets washed away or averaged out to get back to this Einstein result, or to the Fick's law result. And you can imagine here we're only talking about a random walk of 50 steps. Penetrant molecules in a polymer might be executing hundreds of thousands or millions of steps per second, and we're only having 1,000 of these particles being released, whereas in a real system one would have, orders and orders of magnitude more particles undertaking this random walk. And so from a macroscopic point of view, we really never see deviations away from Fick's law or away from the Einstein relation. So that's for you on Canvas if you'd like to play with it a little more to get a better feel for how this works. It's written in Visual Basic, and you're welcome to have a look at that as well. It's quite simple code. And so I want to now go on to the next set of lecture notes and start to discuss the solubility of small molecules in polymers. And so as we open the course, we discussed the idea that the rate of transport of small molecules through a polymer would depend upon how many small molecules one could dissolve in the polymer times how fast they could migrate. In other words, the permeability was a function of the solubility of the penetrant in the polymer times the diffusion coefficient of the penetrant in the polymer. And we've just spent a bit of time talking in general about how diffusion works in a mechanistic sense, and now I'd like to start to talk about solubility, and in particular start to talk about differences between fundamental differences in behavior of solubility of small molecules in polymer, like gases in polymer, water and ions in polymer, drug molecules in polymers. The difference between that situation and the situation where we have just mixtures of small molecules. And this will emphasize the importance of the fact that polymer molecules are large molecules relative to many of the penetrants that would be migrating through membranes or controlled delivery devices and so forth. And it's that vast difference in size that gives rise to fundamental differences in the physical chemistry and the thermodynamics of such systems. And we'll point this out with a system that is shown down here. And so we'll have on the left, a mixture of 50 weight percent styrene and 50 weight percent toluene. So these are low molecular weight liquids, and at a given temperature in a sealed container, the vapor above this liquid will have a certain partial pressure or a certain composition, a certain mole fraction of styrene and a certain mole fraction of toluene, and that will translate to a given partial pressure of, for example, styrene or toluene, and therefore to a given total pressure in that system, since that's just the sum of the partial pressures of the components in the gas phase. And we'll contrast that with another system which now has 50 weight percent polystyrene in it and 50 weight percent toluene. Now, the thermodynamic difference between styrene and polystyrene is that the double bond in styrene has been replaced with single bonds in polystyrene, and the styrene molecules have been hooked together to form the polystyrene. And it turns out that hooking the monomer units together has a profound impact on the thermodynamics of such systems. And we're gonna work our way through that, starting with the thermodynamics of ideal solution, which applies to the case on the left, and then move on to thermodynamics of Flory-Huggins behavior, which is a classic model used to predict solvent behavior in polymers. And so here are the underlying data for the calculation of the total pressure in the headspace above those mixtures. So here's the structure of toluene and styrene. The polystyrene I've just taken to have a molecular weight of 200,000 grams per mole. That's an arbitrary choice, and all I'm really wanting to do is make sure that this number is way larger than the styrene or toluene molecular weight. Here are the densities of the components and the saturation vapor pressures at the temperature of the experiment. The polystyrene, of course, is not volatile, so it doesn't have a saturation vapor pressure at these conditions. And if we start to calculate then the total pressure above the headspace of this liquid in case A, where we have a mixture of styrene and toluene, we can always write the total pressure in case A as the sum of the partial pressures of the components, so the partial pressure of toluene and the partial pressure of the styrene. This is chapter and verse from the Dalton's law. It's a definition of partial pressure in terms of total pressure. Raoult's law will tell us that the partial pressure of any component above a solution is equal to the mole fraction of that component in the solution times the saturation vapor pressure of that component at the temperature of interest. And so this will be the mole fraction of toluene in the mixture, its saturation vapor pressure, and likewise for the styrene. And so we can go about calculating the mole fraction of toluene and styrene in this mixture based upon the weight fractions. It was a 50% styrene and 50% toluene. And we use the molecular weights to convert the weight fractions to mole fractions, and a 50% by weight toluene mixture corresponds to about 53 mole percent toluene, and the balance is styrene. And then we can calculate the total pressure in the headspace above case A is just the mole fraction of toluene times its vapor pressure, and likewise for the styrene, exactly according to the Raoult's law calculation shown here. And the total pressure then above that liquid mixture of toluene and styrene is 24.2 millimeters of mercury. And so if you're came up as a chemical engineer, you would have made these kind of calculations in the introductory mass and energy balance class, and perhaps also again in thermodynamics and maybe even later in separations as well. So I hope this is a familiar concept for you. Now we switch to the case where the styrene has been polymerized to form polystyrene. The definition of the total pressure in that case, what we call case B earlier in the notes, is exactly the same as it was earlier. This definition is independent of the nature of the components in the system. So the total pressure in case B is the partial pressure of the toluene plus the partial pressure of the polystyrene. We've said the polystyrene is not volatile, so it doesn't have a partial pressure, and therefore the total pressure should just be equal to the partial pressure of toluene. And if we follow the same pathway as we did on the previous slide, and that is set the partial pressure of toluene equal to its mole fraction in the liquid phase times its vapor pressure, then we can calculate the total pressure above that mixture. Now, I'm going to make the calculation in this way for the time being, but I will tell you that this is not correct, and it's going to lead to a discrepancy between the experiments and experimental data and the calculation that was resolved in the 40s by a fellow named Paul Flory, who developed a thermodynamic theory to replace this expression essentially with one that was appropriate for polymer solvent systems rather than just mixtures of small molecules. But for the time being, we'll just use the same machinery as we used on the previous slide, because this is what was happening in the 20s and 1920s and 1930s when people were first studying colligative properties of polymer solutions. They were treating them as if they were using the same mixture thermodynamics as are used in small molecules. Now, one thing you'll notice is if you go to calculate the mole fraction of toluene in a mixture that's 50% toluene and 50% polystyrene that has a molecular weight of 200,000, you'll immediately find that the mole fraction of toluene is 99.95% and that of the polystyrene is only 0.05%, even though the solution is 50 weight percent polymer. And so this is the first clue that maybe mole fraction is not going to be the best indicator of what the concentration is of polymer in that mixture. And you can see why this is coming about. The calculation is accurate, and what it reflects is that while the mass of toluene and the mass of polystyrene are equal to one another, the toluene having much lower molecular weight on the order of 92 grams per mole just really outnumbers the polystyrene. And so the vast number of majority of the molecules in that mixture are toluene, and there's only a relatively small proportion of polymer molecules. And so continuing the calculation, we would, along these lines, then calculate the total pressure in case B, that is the toluene polystyrene case, to be very, very close to just the vapor pressure of toluene under these circumstances if we're using ideal solution theory, that is Raoult's law, as shown at the top of the page. And it turns out that an experimental determination of the total pressure, because you can imagine setting up this experiment and measuring that pressure, gives a value of about 33.3 millimeters, which is different, significantly different, it turns out, from 36.91 millimeters. And in fact, you can look at this difference as it's 180 times as large as the decrease anticipated from ideal solution theory. So ideal solution theory would say that, well, because there is some polymer in here, rather than the total pressure being the vapor pressure of toluene, 36.91 millimeters of mercury, the ideal solution theory would predict that the presence of that polymer lowers that total pressure to 36.89 millimeters of mercury, or lowers it by just 0.02 millimeters of mercury. And in fact, the experimental measurement is 180 times as large a decrease as anticipated from ideal solution thermodynamics. And this prompted a crisis in the early days of polymer science because people didn't understand why the usual rules of thermodynamics did not apply to polymer solutions. And in order to understand the science behind the polymer solution thermodynamics, it's helpful to take just a moment and go back and cover briefly the ideal solution thermodynamics and the statistical mechanics of an ideal solution of two components. And so just will remind you that if you have two components, and you can think about toluene and styrene if you wish, or hexane and heptane, the criteria for forming a single phase is that the Gibbs free energy of mixing be negative, and that Gibbs free energy of mixing is defined as the free energy of the mixture minus the free energies of the pure components 1 and 2 before they're mixed. The Gibbs free energy is related to enthalpy H and entropy S by the expression that's shown in the middle of this slide. And so the change in Gibbs free energy is equal to change in enthalpy minus the absolute temperature times the delta S of mixing, where the delta S of mixing and the change in enthalpy upon mixing are defined in exactly the same way as the delta G of mixing. Now, we're going to attack this problem statistically, and so we need a linkage between the molecular or statistical point of view and macroscopic thermodynamics, and that link is provided by Boltzmann, who argued that the entropy of an assembly of molecules was proportional to the logarithm of the total number of distinguishable equal energy arrangements of the molecules, what he called omega, and the constant of proportionality is the so-called Boltzmann's constant. And there's a little picture of Boltzmann watching over us. And if the pure solvent and pure polymer were mixed to form a solution, then the entropy change on mixing could be written as shown here. This would also be true if it were two solvents that were mixed together. So this is a very general relationship. And you may have heard this, but here it is on Boltzmann's grave, is this relationship between the microscopic or statistical world, omega, and the world of macroscopic or continuum thermodynamics, entropy. I thought that was, he must have been, felt particularly strongly about this idea. In any event, in an ideal solution of small molecules, and we imagine one of them being these black filled circles and the other being the open circles, the molecules are taken to be, in the simplest case, of being essentially identical in size and having essentially the same external force field, and often we see pictures of these lattice type arrangements that are used to represent such solutions. And it turns out that you can get rid of the lattice and not have the molecules so confined as might be suggested by this two-dimensional lattice, and still get the results that we're going to show, but it provides a really convenient and easy way to see how these solution thermodynamics develop. And so we imagine a mixture being these white and red spheres, if you will, sitting at regularly defined positions in this lattice. And the ideal solution theory also supposes that a similar lattice, this is the lattice for the mixture, can be used to describe the arrangements of the molecules of type 1 in the pure state, molecules of type 2, as well as their mixtures. And this has the really important practical drawback is that it doesn't allow any volume change on mixing. And it requires the size and shape of the molecules of type 1 and 2 to be virtually identical. Now, more sophisticated models relax these assumptions, But we'll start with the simplest case because we can work that one out analytically, and it provides a really good background or contrast to use for the polymer case. From combinatorial analysis, we can calculate the number of distinguishable arrangement of placing N1 molecules of component 1 and N2 molecules of component 2 on a lattice with N1 plus N2 sites. And so we imagine that this is the lattice with N1 plus N2 sites, and at each lattice position there's either a molecule of type 1 or a molecule of type 2. And there's N1 molecules of 1 and N2 molecules of 2. And so that's this is the number of distinguishable ways of placing N1 identical molecules of type 1 and N2 identical molecules of type 2 on a lattice. This is again combinatorial analysis that I think you've probably seen quite a ways back in your education. The pure components, since all the molecules of 1 are the same and all the molecules of 2 are the same, they can only be arranged on their lattices in one distinguishable arrangement. And so we calculate the delta S of mixing for mixing N1 molecules of type 1 and N2 molecules of type 2, and according to the Boltzmann relationship, the result is shown here. Because omega 1 and omega 2 are 1, these log terms go to 0, and the delta S of mixing is just k log omega 1, 2. We have the expression here for omega 1, 2 that we can put into in place of omega 1, 2, and now write it in terms of the number of molecules of type 1 and type 2. We use Stirling's approximation again because the numbers of molecules are going to be extremely large, and so we can approximate the log of the factorial in each case as shown here. And if we apply Stirling's law, you should verify that the result that we get is shown here. Ideal solutions by definition are those which have no enthalpy change on mixing, and so the delta G of mixing, which is equal to delta H of mixing minus T delta S of mixing. If the delta H of mixing is 0, then the delta G of mixing is just minus T times the delta S of mixing, or it's minus T times the expression that's shown here. And so that's what we have at the bottom of the slide. We can use this expression for the free energy now to calculate the chemical potential or thermodynamic activity of component 1. And the definition of the chemical potential of component 1 at a given temperature, pressure, and composition relative to its reference chemical potential is just the RT times the logarithm of the thermodynamic activity of component 1. And what's on the right-hand side here is an exact thermodynamic identity that relates the chemical potential, or effectively the activity, to changes in the Gibbs free energy upon mixing, with changing the number of molecules of type 1, constant temperature, pressure, and holding the number of molecules of type 2 constant. And so we have the expression for the delta G of mixing shown here. We can put that into this derivative, and you should verify that the result is shown here. I'll rewrite Boltzmann's constant in terms of the gas law, because the gas law constant R is just Avogadro's number times K. And then we have an expression for RT times the log of A, and it's written in terms of the number of molecules of type 1 divided by the total number of molecules of type 1 and 2 which are in the mixture. This is then by definition the mole fraction of component 1. Number of molecules of 1 divided by total number of molecules is the mole fraction of 1. And we simplify this expression, and it says that the thermodynamic activity of an ideal solution is equal to thermodynamic activity of component 1 in an ideal solution is equal to its mole fraction in that solution. And A1, the activity of component 1 in the gas phase, can be further related to the ratio of the partial pressure to the vapor pressure of component 1. And from this, these two relationships, you can derive Raoult's law. So it's the partial pressure of component 1 above a liquid mixture that has a mole fraction, a liquid phase mole fraction of component 1, the partial pressure in the gas phase above that mixture is the mole fraction of component 1 in the liquid phase times the vapor pressure of that component. So this is just a quick derivation of Raoult's law showing how you get that from ideal solution thermodynamics. And we provide that as background now to go into the situation with polymers. Before we do that, we'll come back and just get a couple of extra relationships that'll be really helpful to compare with the polymer case a few slides from now. So we'll write the Gibbs free energy of mixing in terms of numbers of molecules, numbers of moles of molecules of type 1 and 2 rather than numbers of molecules directly, and then also write it further in terms of the mole fractions of component 1 and 2. And so these are the relationships for the Gibbs free energy of mixing and the delta S of mixing for an ideal binary solution. And where again N1 and X1 are the number of moles of component 1 and the mole fraction, and likewise for component 2. The delta H of mixing is equal to 0 for an ideal solution. Now we'll pass on to the polymer solution case and consider a situation where you have a polymer that is dissolved in solvent. And the key intellectual contribution among many, but a key intellectual insight that Paul Flory had was that ideal solution theory is based upon molecules 1 and 2 having the same or very similar size, and this is really not the case with polymer solvent mixtures where the polymer has any significant molecular weight at all. And so Flory and Huggins, working independently actually, modified the treatment we've just gone through to account for the very different size between the polymer molecules and solvent molecules. Here's a picture of Paul Flory. He had a long and storied career, started work in the polymer field with Wallace Carruthers at DuPont. Carruthers was one of the fathers of modern synthetic polymer chemistry. He developed the chemistry behind nylons and polyesters that really built DuPont's polymers business and ultimately other polymer companies as well, when DuPont, for antitrust reasons, had to divest, had to share their technology with other companies. Flory worked on synthetic rubber during Second World War in the U.S., and after a considerable time in industry, eventually wound up at the chemistry department at Stanford University in California, where he finished his career, won a Nobel Prize in chemistry for the work that we're about to describe. And it's known, this work is now known today as the Flory-Huggins theory, and it's an extension of ideal solution theory in components that have a wide variety of widely varying size. And so take the simplest case is a mixture that has N1 solvent molecules and N2 polymer molecules, and we're going to use the same lattice-based concept that we saw just a moment ago. Each of these N2 polymer molecules has X segments to it, and each segment is assumed to occupy one lattice site. Each solvent molecule is also assumed to occupy one lattice site. X is often taken as the ratio of the molar volume of the polymer to the solvent, and you'll often see it said in many texts equal just to the degree of polymerization of the polymer. That is, how many monomer units are in a given polymer chain. And so you can think about X being the number, approximately the number of monomer units that are in a given polymer chain, and each monomer unit occupies one lattice site like a solvent molecule. So on this lattice there are N1 sites for solvent and X times N2 sites for polymer. And throughout the rest of this discussion, component 1 is always going to be solvent. Component 2 will always be polymer. And if we now look at the lattice, one that's similar to the one I showed earlier, except now we're dealing with circles and squares rather than black and white circles to represent the different molecules. There's a striking difference between the small molecule solution and a polymer solution that has essentially the same number of solvent molecules and the same number of monomer units, but now the monomer units are connected into a polymer chain. And you can see offhand what a key result of this theory is going to be, and in a qualitative sense. On the left-hand side, the position of one of these squares on this lattice is essentially independent of the position of any of the other squares, provided that there's an open site on the lattice for this particular square to fit into. The situation is not the same, for example, for a square that's shown here. It can't go into any just any slot it wants to, because it's connected by covalent chemical bonds to two neighboring squares, and it has to stay with them. And so what this is going to mean from a thermodynamic point of view is that the number of ways of arranging the squares in a case where they're all connected together is going to be much less than the numbers of ways, of distinguishable ways of arranging the squares if they're not connected at all. And that means that the delta S of mixing of polymer solutions is going to be much less than the delta S of mixing of small molecule solutions. And you'll remember that the Gibbs free energy of mixing, if there's no delta, no enthalpic effects, the Gibbs free energy of mixing is just minus T times delta S of mixing. And so if you make the delta S of mixing really small, then as you combine two components like polymer and solvent, with the criteria that the mixture be miscible is that delta G of mixing has to be less than 0. With high polymers, they are going to be much less likely to be soluble in a given solvent than they would be if it were just a collection of disconnected monomer units. And in fact, this is what we routinely observe in polymer science, is that if you have a monomer that is soluble in a solvent and you start to polymerize the polymer in that solvent, in many cases the polymer will eventually phase separate out of solution. It doesn't want to be dissolved in that solvent the way the monomer would. And what's going on there is that in the monomeric state, the delta S of mixing is just so high that the monomer and solvent will mix together. But when you start to polymerize the monomer to form polymer chains, the delta S of mixing goes way down, and you may get to a situation where the polymer actually phase separates during polymerization, and that's the foundational basis for this. Now, in order to calculate the delta S of mixing, which is a key component in this model, we have to calculate the numbers of ways of arranging all of the solvent, the N1 solvent molecules and the N2 polymer molecules on that lattice. And so the way the lattice will be imagined is that it has N1 sites for the solvent, and each of the N2 polymer chains has X monomer units, if you will, and each of those monomer units takes up a site. So it has X times N2 sites for the polymer chains. And we start with the lattice empty and start to place polymer segments one by one on each of the polymer chains. And we haven't put any solvent onto or into the lattice at the beginning. And so we imagine a case where we've already put I polymer molecules have been added to the lattice at random. And as a result of that, there remain N1 plus Xn2, that's the total number of lattice sites, minus X times I. We put down I polymer molecules. Each of them have X, take up X sites. And so minus Xi is the amount of sites that have been taken up by the polymer molecules. And so the total number of vacant sites at N1 plus Xn2 is reduced by Xi. And it's one of these remaining open sites that can accommodate the first segment of molecule I plus 1. And if this is a purely random process, any of these open sites can accommodate that first segment of molecule I plus 1. We've also assumed that there are a number of lattice positions surrounding a given lattice position or cell, and that number is called Z, the coordination number. You might imagine, for example, in this simple case, that Z, if in a planar case, might be 1, 2, 3, 4. That is, once you've placed one molecule here, that there would be 4 neighboring sites. If you imagine this being in 3 dimensions, then there would be one above this one and one below it for perhaps a total of 6. It turns out that the exact value of the coordination number has very little bearing on the final answer, but that's what this term Z means. And so after we place the first segment of molecule I plus 1 into one of the open lattice positions, the second segment of that chain can only be placed in one of the Z surrounding sites that are not already occupied. And so if you think about that for a second, if you place the first segment into one of the open sites as shown here, if that second segment weren't connected to the first segment, it could go into a bunch of sites, N1 plus Xn2 minus Xi minus 1. But because the second segment of the polymer chain is connected to the first segment, it can only go into a few of the surrounding sites that are nearest neighbors, these so-called Z surrounding sites, and it can only go into those that are not already occupied. We'll let F sub I, following Flory, be the probability that a given cell which is adjacent to a previously vacant cell, such as the one occupied by segment 1 of molecule I plus 1, is occupied. So this is the fraction. It's a probability that a given cell is occupied when the lattice has has a certain number of its sites filled and the remainder of them open. So the probable number of open lattice sites for segment 2 of molecule I plus 1 is Z times 1 minus F sub I. So if the coordination number, for example, is 6, if you imagine that cubic coordination we talked about a moment ago, and if half of the lattice cells are already occupied, then the probable number of open sites for segment 2 of molecule I plus 1 would be 6 times 1 minus a half, or it would be 3. The probable number of sites for the third segment of this molecule is Z minus 1 times 1 minus F. So it is exactly the value that's shown here, except we have to recognize that when we have 3 segments, when we're trying to place that third one, there is already somebody sitting in one of the open sites that surround it, and that would be segment 2 of molecule I plus 1. And that was not the case when we're placing that very first the second segment, because it can take on any of the open cells around segment 1. But when we start to place segment 3, it can only fit into Z minus 1 of the open sites, because for sure one of the sites next to segment 3 is going to be occupied by segment 2. And so then Flory took every succeeding segment of that polymer chain, took the probable number of sites to be equal to the same as it was for that third segment. And this will ignore the situation where a segment of the same chain occupies one of the sites under consideration. So, you know, if you are laying down the chain segments randomly and a loop is formed, then, you know, you could eventually get to a situation where you're trying to place a segment into a slot or a lattice position that's already occupied by a segment of the same chain, and that possibility is ignored. Later versions of the Flory-Huggins theory, modifications to it, came back and have attempted to correct for that, but that's beyond the scope of our discussion today. The total number of ways of introducing these X-connected or contiguous polymer segments of chain I+1 onto the lattice, so-called noose of I+1, is the product of the ways of placing every segment. So again, this is a combinatorial problem. So how many ways can you place the X segments of chain I+1? The number of ways you can, distinguishable ways you can arrange that on the lattice is just equal to the number of ways of arranging the first segment times then the number of ways of arranging the second segment times the number of ways of arranging segments 3 through X. A little bit of algebra turns this expression into this one. And so this gives you the total number of ways of arranging chain I+1 on the lattice. The number of ways of arranging all of the polymer molecules, if they're indistinguishable on the lattice, is the probability of is the product rather of the number of ways of arranging each of the polymer chains, and then divided by into factorial, so that we don't treat them as don't treat the polymer chains as distinguishable. And so to complete this model, Flory needed an expression for the probability that a cell is empty adjacent to a cell that's just been filled with a segment. And here Flory made an approximation that has received a lot of criticism in the literature. However, to a good approximation, for many practical circumstances, it provides a very good agreement, or much better agreement with the experimental data than anything that was possible beforehand. And so Flory just said that the probability of finding an open cell next to cells just been filled with a segment is just equal to the fraction of vacant sites over the entire lattice. So here's the total number of lattice sites, here's the number of lattice sites that have been filled after placing I polymer molecules, and then here's the total number of lattice sites again. So he just made a simple approximation for the probability of finding an empty cell. And this you'll find in the literature referred to as a mean field approximation. And it is not so valid in dilute solutions where the polymer chains are well separated from one another and where there's likely to be not a very homogeneous or continuous distribution of concentration of segments as you move spatially through the solution. And it tends to be much more valid in highly concentrated systems where the concentration of monomer segments is more uniform spatially. And so this is the expression for the number of ways of placing polymer chain I+1 on the lattice, the expression for the probability of finding an open lattice site, and then if these two are combined, you get the expression that is shown here after just a bit of algebraic rearrangement. Flory made the following mathematical simplification, which in fact at the end has essentially no bearing on the results. He replaced z by z minus 1. There's no physical reason to do that. It just makes the mathematics a little bit simpler, because then this becomes z minus 1 to the x minus 1, so it can be loaded into the numerator of this expression, and the top piece can come out to go with this one to give this expression raised to the x power. And over the next few slides, we're going to walk through the the algebra to get to the final result. I will tell you, I won't expect you to reproduce this on any sort of timed exam or anything like that, but I think it's very helpful if you're going to work in polymers, to have seen this at least once and to have an appreciation for where it comes from, because it then gives you an intuition about how solution thermodynamics work in polymers, and also gives you an appreciation when we talk a bit later about improvements on this model, about what assumptions and restrictions are being relieved as a result of making those improvements. Flory also rewrote the beginning part of this expression in terms of factorials as shown here, and you can see that that this equivalency is reasonable if you start to write out these factorials as shown here, and eventually when the numbers of molecules get to be really large, this term essentially becomes equal to this one, and it turns out to be a good approximation. And so that gives the following expression for the number of ways of arranging polymer molecule I+1 on the lattice. With this, we then come to calculating the number of distinguishable ways of arranging all of the polymer molecules on the lattice. And so it's just 1 over n2 factorial times the product of nu sub I+1 over all of the polymer molecules. So the number of distinguishable ways of arranging all of the polymer molecules, all of the N2 polymer molecules on the lattice, is just equal to the probability of the number of ways of arranging the first one times the number of ways of arranging the second one, given that the first one is already present, and so on and so forth. Again, there's some algebraic manipulation that goes on to simplify omega 1, 2 as shown here. The next step is to simplify the product sign, the terms in curly brackets here. And this next simplification, if I just write it out directly, it's not quite clear how it happens, and so I'll write out several terms of this product sign, starting with I equals 1, 2, and 3, and then jump all the way to the end where I is equal to the final into the final polymer molecule going down on the lattice. And what you'll see in this in the first case, this is the number of ways of arranging the first polymer molecule on the lattice. When I is equal to 1, this term goes away, and this one just goes to x. And so what's left is this. I can write out the factorial n1 plus xn2 as n1 plus xn2 times n1 plus xn2 minus 1, n1 plus xn2 minus 2, so on and so forth, all the way down to n1 plus xn2 minus x plus 1 and n1 plus xn2 minus x. And when I get to that point, every term from here on is canceled by a term in the denominator of this expression. And so that first expression for the number of ways of arranging polymer chain 1 on the lattice basically stops after this point, next to the last term. Likewise, for the number of ways of arranging the second polymer molecule, I can write it out in exactly the same way, and it starts at n1 plus xn2 minus x times n1 minus xn2 minus x minus 1, and so on and so forth, until you get down to the term that cancels with the denominator. And likewise for the third term. And now if we come back and look at what terms are remaining. So for the I equals 1 case, it starts at n1 plus xn2 and then counts backwards to n1 plus xn2 minus x plus 1. For I equals 2, it picks up at the next term, right? n1 plus xn2 minus x plus 1. Then first term in I equals 2 is n1 plus xn2 minus x. And remember, these are all, with this product sign, these terms are all multiplied together. So we have just a string of these guys being multiplied together. And likewise, the last term that survives from the I equal 2, number of ways of laying down the second polymer molecule, is just one ahead of the first term in the I equal 3 term of this curly brackets. And finally, down at the last term is shown here. And if you put this together, what you will find is that this term can be replaced by n1 plus xn2 factorial over n1 factorial. And you can see that n1 plus xn2 multiplied by n1 plus xn2 minus 1 minus 2, so on and so forth, minus x plus 1, minus x, on and on and on, until you get down to n1 plus 1 factorial over n1 factorial. And so this relationship can be written as shown here. It's no different to write n1 factorial than it is to write n1 plus x in 2 minus x in 2 factorial. It's exactly the same thing. And so the number of distinguishable configurations of putting the polymer segments down on the lattice is given by the expression that's at the bottom of the page. And this really is a key result. It's going to unlock the rest of the theory for us. So that's the heavy lifting is over. And so we recall that the entropy of mixing, the entropy S12 of the mixture is K times omega, log of omega 12. We use Stirling's approximation again because N1, N2, and X are going to be very, very large. And we start to put this expression in for S12, the entropy of the mixture of monomer and solvent. And then there's a couple lines of algebra here that I will not belabor to get to the expression that is shown here, or equivalently the one at the bottom of the page is the entropy of mixing all of the polymer segments of each chain on the lattice. Now, Flory envisioned that the pure solvent would fill the lattice with only one distinguishable arrangement. That is, once you had the polymer chains laid out on the lattice randomly, that the solvent would just be sprinkled into whatever sites that were left, and there'd only be one distinguishable way to arrange the solvent. Since the solvent molecules are indistinguishable, there's only one way to fill the remaining lattice sites, and so S1 doesn't make a contribution ultimately to the entropy change on mixing. However, the pure polymer, absent any solvent, could be arranged in many distinguishable ways on the lattice, and so on its lattice. And so Flory just took the same expression he had used for laying down the polymer segments one by one on a lattice that has N1 sites for solvent and Xn2 sites for polymer. He used that same expression, but now just set N1 equal to 0. And so he calculated the number of ways of laying down the polymer segments based upon the expression he used for laying down the number of polymer segments in the case where solvent were present, and he just set the number of solvent sites equal to 0 for that calculation. And then again, using Stirling's approximation and the Boltzmann relationship, you can derive the expression at the bottom of the page for the entropy associated with the pure polymer. Then this is the entropy associated with the polymer solvent mixture, the entropy associated with the pure polymer, the entropy associated with the solvent is equal to 0, as we argued earlier, and the delta S of mixing then can be calculated as S12 minus S2. You see some of these terms canceling, and what you're left with is a very simple expression, which is absolutely remarkable. It's minus the Boltzmann's constant times the number of solvent molecules times the logarithm of the solvent volume fraction. Now, the way this is defined is it's the number of solvent molecules times the number of solvent molecules plus the number of polymer molecules times the number of segments plus segments per polymer molecule. So this is the number of solvent molecules, and this is the total number of sites on the lattice. And if each of the segments, the solvent molecules and the polymer segments, have essentially the same volume, then this is proportional to the volume occupied by the volume occupied by the solvent divided by the total volume of the system, or it's a solvent volume fraction. Phi2 likewise is the polymer volume fraction. Now, if X, that is the, if you will, number of degrees of polymerization in the polymer, were equal to 1, then this would be number of solvent molecules divided by number of solvent molecules plus number of polymer segments. It would just be the mole fraction of solvent, and that would be exactly the same as we got for the ideal solution theory. So the difference between the ideal solution theory and the Flory-Huggins theory in terms of the entropy change on mixing is the inclusion of this term X that has fallen out of Flory's analysis, and it converts these what would be mole fractions here in ideal solution thermodynamics, it converts them to volume fraction, and that turns out to be all the difference in terms of calculating thermodynamic properties of polymer solutions. And so if we put this now on this basis, with Boltzmann's constant, N1 and N2 are numbers of monomer, numbers of solvent molecules and numbers of polymer molecules. We can now put that on a number of moles of solvent and polymer, lowercase n1 and n2, and then Boltzmann's constant becomes R. Boltzmann's constant times Avogadro's number becomes R. And if you compare that to the ideal solution result, the only difference is the replacement of mole fractions in the ideal solution result with volume fractions in the polymer solution result. And in the limit when X is equal to 1, that is the polymer molecule and solvent molecules are the same sizes, the Flory-Huggins result reduces to the ideal solution result that we derived for to get Raoult's law back at the beginning of this lecture. And Flory recognized this. So this is his classic paper where he derives the relationship that I just showed you along much of the lines that I showed you. So I put that derivation together based upon information that's in this paper, and also he has he wrote an extremely clear book on polymer science, and if you have interest in any of Flory's work or polymer science in the early days, reading Flory's book is probably the clearest place. He had an extraordinarily great way of explaining information that was that's clear and accessible. You'll often see work from that book summarized in other articles and textbooks and so forth, and none of them are as good or as clear as the original version of Flory's work. Now, there's a little bit of nomenclature issue here. So equation 1 is the ideal solution result for fluorine, and instead of using lowercase x for mole fraction, he uses uppercase X. And in the polymer case, instead of using Phe1 and Phe2 as solvent and polymer volume fractions, he uses V1 and V2. And he noted that it's interesting to note that 10.1, that's the expression for the delta S of mixing in the polymer solvent system, is so similar in form to the ideal solution result. Replacement of volume fractions by mole fractions, and the log of the former yields the latter. And he goes on to say the entropy of mixing of polymer and solvent, that's this one, is less, and it's far less than that for mixing the completely dissociated polymer segments with solvent, which would be given by this expression. And that goes on to qualitatively and ultimately quantitatively describe a lot of the properties of polymer solutions. Now, in order to finalize this discussion, we need to make a statement about the delta H of mixing. It turns out that it doesn't, Flory did not leave the delta H of mixing term equal to 0 the way we did in ideal solution thermodynamics. It turns out that to describe a wide variety of polymer solvent interactions, you really do have to account for the enthalpy change on interactions. Originally, the delta H of mixing was calculated assuming that only nearest neighbor interactions contributed to this. And also, he went back to popular at the time lattice theory to estimate the value of the delta H of mixing. And so he estimated that as essentially the enthalpy change on forming two solvent segment nearest neighbor contacts or interaction occurs by disrupting one solvent-solvent and one polymer-polymer contact. And so his expression for the delta H of mixing is equal to P12, which he called the total number of solvent segment contacts in solution. And these W12 is the potential energy of interaction between solvent and a polymer segment. 11 would be between solvent and solvent, and 22 would be between polymer segment and polymer segment. And I'll show you where this comes from in just another slide or two here, which will make that real clear. So the delta W12, which is just the piece of this that's not in that's in parentheses, is defined this way. Lattice theory would assume that before you have a mixing of two components, 1 and 2, and this is widely used in low molar mass mixtures, so you won't see any of the two molecules connected in this case. But in order to mix molecules 1 and 2, or more specifically, in order to take one molecule of type 1 and put it into an environment of type 2, and take one molecule of type 2 and put it into an environment of type 1, involves a certain change in energy. And so the energy absorbed in taking one segment of one solvent molecule and putting it into a bunch of polymer, or taking one polymer segment and putting it into a bunch of solvent, is governed by the following thermodynamics. So when you put one molecule of type 2 in here with 4 nearest neighbors, you form 1, 2, 3, 4 interactions of type 1, 2. That's 1, 2, 3, 4 interactions of type 1, 2. Likewise, when you take a molecule of type 1 and drop it into a sea of molecules of type 2, you form 1, 2, 3, 4 interactions of type 1, 2. So you form a total of 4 new interactions of type 1, 2 plus 4 more, or 8 interactions of type 1, 2 when you take a molecule of type 1 and put it into 2 and a molecule of 2 and put it into 1. You form 8 interactions of type 1, 2, and you break 4 interactions of type 1, 1. That's these 4 here. And you also break 4 interactions of type 2, 2. That's these 4 here. And this is where the expression in parentheses comes from. And in this case, 8 would be the the total number of solvent segment contacts around a given location in solution. And so the number of these solvent segment contacts then Flory wrote as being equal to the number of polymer molecules. And the picture here is you have a polymer chain now surrounded with all of the lattice positions around it now filled with solvent. And so how many contacts are there between polymer and solvent? Well, for each of the interior polymer segments, that is the segments except those on the end, they would see solvent around them at Z minus 2 locations. That is, any interior polymer segment would have in two of the lattice positions around it, it would have polymer segments, and then in all of the other accessible lattice positions could have solvent. At the end of the polymer chain, then the ends of the polymer chain only have one segment next to them that has to be polymer, and so on each end you get an extra potential polymer solvent contact, then multiplied by the total number of polymer molecules. This would be the maximum number of polymer solvent segmental contacts. And Flory then said, well, on average there is a certain volume fraction of solvent, and so the maximum number of potential contacts times the volume fraction of solvent is his estimation for the number of solvent segment contacts. So when the volume fraction of solvent is high, approaches 1, then the number of solvent segment contacts approaches this maximum value. And when there's a lot of polymer in there and the volume fraction of solvent is low, then some of the polymer segments are going to be next to polymer segments on other chains and not next to solvent molecules. That's what this last factor reflects. And then he made the approximation shown here, neglecting basically the 2 for large, high molecular weight polymers, so high degrees of polymerization. And so with this expression for the delta H of mixing and the expression for the number of solvent segment contacts that come in, here's our definitions of the volume fractions of solvent and polymer. And these definitions lead to the mathematical relationship that's shown here, and you should verify that. But in fact, that's the case. And so we can rewrite the number of polymer solvent segment contacts as shown here, and the delta H of mixing then takes on the final form that's shown here. Now, Z, this number of is basically coordination positions or accessible lattice positions around any given segment that might have, another polymer segment or a solvent sitting in it, and this interchange energy are closely related, and it's essentially impossible experimentally to calculate them independently. And so Flory lumped these two parameters together in a parameter that he called chi. And so basically chi just is this last piece of the delta H of mixing. divided by KT. And so then the delta H of mixing can be written as shown here on a molecule basis, or we can put it on a molar basis by writing R is K times Avogadro's number, as shown here. Then the delta G of mixing is the delta H of mixing minus T delta S of mixing. And so this is the final expression for the delta G of mixing in Flory-Huggins equation. So here's the entropic part. This is the delta S of mixing, and this is the delta H of mixing. Now, this model has an anachronism in it, or a tension in the derivation. In order to have this expression for the entropy, one has to assume that polymer segments and monomer and solvent are basically have the same interactions for each other as for themselves as they have for each other. And so there's no particular affinity for the solvent to want to stick together, or the polymer chains to want to stick together, or the polymer chains to want to go after the solvent and stay with the solvent rather than with other polymer chains. And that is the result that leads to this random mixing expression for the delta S of mixing. The minute that you introduce a term that allows there to be differential energy of interaction between the polymer and solvent, now you start to make either the solvent wants to stick to itself. Energetically, it's more favorable for the solvent to be close together. It's more favorable for the polymer segments to stay together, or the polymer segments and solvent would rather be with each other than with of the molecules their own kind. Having this term present will necessarily throw off a little bit this calculation of the entropy, because if you have associating components, because they don't have delta H of mixing equal to 0, then the mixing won't be completely random as given by this expression. And so this was a criticism of the Flory theory, and there have been various attempts to modify this expression to account for the non-random mixing that would come about if you have delta H of mixing, if you have differences in the energy of interaction between solvent and polymer. It turns out that that most of those attempts to correct the basic Flory approach never really gained the traction that Flory's original work did. And so we'll proceed along with the Flory-Huggins model, but just understand that is a criticism of this particular model. Often this parameter chi is treated to a certain extent as an adjustable empirical parameter, and in many textbooks you'll see this the fact that if the delta H of mixing is not equal to 0, that has an implication for how it changes the delta S of mixing. And so you'll often see chi written as chi sub H plus chi sub S, where chi sub H represents the enthalpic contribution to chi, and chi sub S represents entropic contribution. This is really a more or less empirical adjustment to Flory's original theory to account for this feature that we just talked about. But this was the first widely accepted attempt to explain polymer solution thermodynamics based on the vast size difference between polymer and solvent molecules, and it's the basic framework to describe polymer solution thermodynamics in many different cases, not only the ones that will be of interest to us. Coming to the end of the discussion with the expression for the delta G of mixing from basic thermodynamics, and then Flory's model shown up in the upper right hand side, we can now come back and calculate the thermodynamic activity of the solvent in a polymer solvent mixture, and we do that exactly the same way as we did it for small molecule mixtures by taking the derivative of delta G of mixing with respect to N1, holding everything else constant. And if you take that derivative of Florey's model, the result is shown here. This is the classic Florey-Huggins expression. The logarithm of the solvent activity is equal to the log of the solvent volume fraction plus 1 minus 1 over x times the polymer volume fraction plus chi times the polymer volume fraction squared. And in high molecular weight polymers, the degree of polymerization x is often so large that this term 1 over x is negligible, and you'll often see the second term just written as phi2, the volume fraction of polymer. So how is this useful for us? Well, we can use this to describe the partitioning of gases into polymer. And so this is an example of butane absorbing into polydimethyl siloxane or silicone rubber. So what's plotted on the x-axis is the concentration of butane in the polymer, and it's in cc's of butane at STP. And remember that there's 22,414 cc's of any gas in a mole, so this is essentially moles of butane per cc of dry polymer. That's a common way of reporting gas uptake in polymers, and it's plotted as a function of pressure. Fugacity is written on the x-axis here, but that basically just accounts for the fact that particularly at low temperature, butane can be rather non-ideal, and plotting versus fugacity rather than pressure corrects for that non-ideality. The lines through the experimental data are fits to the Florey-Huggins model with 1 over x set to 0 and chi set to be 0.34. So one value of the chi parameter gives the curves that essentially completely describe this experimental data. The relationship between fugacity and activity is that the activity of the butane is equal to its fugacity or pressure divided by its saturation fugacity or saturation pressure. And so we can plot the data not against pressure, but against the ratio of pressure or fugacity, if you will, divided by the saturation value. And then you get a universal curve for the gas uptake versus activity with a single value of chi that describes the data over the entire range of thermodynamic activities that were accessible and over a wide temperature range. And so this is really helpful. And what it says is, based upon these types of calculations, is that once you've measured, for example, just one of these isotherms, the data at one temperature, you can now predict the solubility of gases in polymers at practically any other temperature you want using this simple model with a constant value of chi. It's absolutely remarkable. And remembering that the rate of transport, for example, of butane through polydimethyl siloxane depends upon the solubility of butane times the diffusion of butane, this is the way you can model solubility of gases in rubbery or flexible polymers using this Florey-Huggins model. And it's one of the first stopping points in this kind of modeling. There are more sophisticated methods that can be applied, and we will talk about those. But this is a very simple model and gets very good quantitative results in this case. The estimation of the chi parameter we talked about a little bit earlier, and it has been what's been done historically is to turn to work of Joel Hildebrand. And so Joel Hildebrand was interested in understanding solubility of gases in liquids, and he studied this for many years, decades, in the chemistry department at the University of California at Berkeley, and became probably the most widely recognized expert in gas solubility in liquids. Some of the important practical work he did was for the U.S. government. He designed the breathing gas mixtures for divers that were working at extreme depths. And so as you go down in scuba dive, for example, in deep water, it's easy to have too much nitrogen dissolve in your bloodstream, and this leads either to nitrogen narcosis or if you come up too quickly, to the bends, which can be fatal. And Hildebrand worked with the military to replace nitrogen oxygen mixtures with helium oxygen mixtures for deep sea diving. And helium has a much lower solubility in liquids, in water and polymers and blood, than does nitrogen. Has no detrimental physiological effects. And so with a helium oxygen mixture, one can dive much further and has less problems with the bends. And that comes about from Hildebrand's work in understanding molecular factors involved in gas solubility in liquids. And so Hildebrand's model for estimating the delta H of mixing, enthalpy change on mixing for small molecule liquid mixtures is shown here. And I won't go through the derivation of this because it's I think it's beyond the scope of what we need to do. V sub m is the molar volume of the mixture. Phi1 and Phi2 are the volume fractions. Delta 1 and delta 2 are the solubility parameters of the two components that are mixing. In the case of a polymer solvent mixture, delta 1 would be the solvent solubility parameter, and delta 2 would be the polymer solubility parameter. And these solubility parameters are defined as the internal energy, a square root of the internal energy on complete vaporization divided by the molar volume of the component. And that can be written in terms of the delta H of vaporization minus RT over the molar volume. And so for small molecule liquids, based on the delta H of vaporization and the molar volume, you can calculate the solubility parameters. Polymers don't evaporate, and so you can't calculate the polymer solubility parameter by this approach. So I'll show another way of doing that here in a moment. But this term, the square of these solubility parameters, is often called the cohesive energy density of a component, and it characterizes the strength of attraction between molecules of a certain type. If you imagine, for example, that a given substance has a very high delta H of vaporization, which would correspond to a high value of solubility parameter, what that would be saying is that the molecules of type I really stick to one another and don't want to vaporize. And so it requires a lot of energy to get them to vaporize. That means they have high cohesive energy density, high level of energy favoring cohesion or favoring the molecules to stick together. So in the Flory-Huggins model, Flory set the enthalpic contribution of chi based on Hildebrand's theory to the expression that's shown here, where V1 is the solvent volume fraction, delta 1 and delta 2 are the solubility parameters for the solvent and polymer. The entropic contribution to chi is often empirically set to a number of about 0.34, and so this is an expression that is in the middle of the slide is the expression it's often used as for chi in many textbooks. Just some key values. Thermodynamic miscibility study show that for polymer solvent systems to be completely miscible, then chi H has to be less than the value that's shown here. And so for high molecular weight polymer, it's essentially that the chi value has to be less than a half. And so when chi values are low, it means that delta H of mixing values are low, and that you see random, more and more random type mixing, which favors mixing of polymer and solvent. So low Chi values favor high solubility of polymers and solvents and polymers and solvents. Now let's go back just to end this discussion. We come back to the beginning of the section and apply the Flory-Huggins treatment to calculate the pressure, total pressure above a 50-50 weight mixture of polystyrene and toluene. Now, instead of calculating mole fractions of toluene and polystyrene, we're going to calculate volume fractions. So we use the density to convert the weight fractions to volume fractions. And the volume fraction of solvent then is 0.541, 54.1%. Toluene, and the volume fraction of polymer now is 45.9%. The log of the activity of toluene is equal to log of the volume fraction of toluene plus the volume fraction of polymer, plus Chi times the square of the volume fraction of polymer. Values for Chi for the polystyrene toluene systems are about 0.25, so toluene is a good solvent for polystyrene, and then the activity of toluene can be calculated from this expression, just plugging in the numbers, and it's about 0.902. And if you then calculate the total pressure as the activity of toluene times its saturation vapor pressure, you get the total pressure is 33.3 millimeters of mercury, and this now is in very good agreement with the experimentally determined pressure value for this particular experiment. And so that's it for this lecture. It's a bit longer than maybe one class period, but I think it's important to see this all at one time and to get a coherent picture of it. Thank you for your time.